Chapter 11 is the last chapter of Calculus 2, but it is a doozy. So section 11.1, we start off talking about sequences, which by themselves are actually not very complicated at all, but can be made complicated. The basic definition of a sequence is it's a list of values. It doesn't actually have to be values. It could be any mathematical object. I could have a sequence of functions. I could have a sequence of matrices. I could have a sequence of vectors. Or I could just have simply a sequence of numbers. We typically deal with numbers, but they'll be represented as functions. So more specifically, a sequence of real numbers is an enumerated list, is a list of real numbers enumerated by the integers. And this could be anything, really. One of the best ones to start talking about is, let's suppose a sequence a sub n is equal to 3, 1, 4, 1. Let me know when you recognize the sequence. Well, since nobody said anything, I just stopped here. But you might recognize that this sequence is the digits of pi. A sub n is equal to the nth digit of pi. Specifically in the notations, I should have braces around that if I'm going to list everything out. Versus this equation here is describing what the nth entry will look like. Similarly, if I suppose I had b sub n is equal to some kind of a function, I could have b sub n equal to 1 over 2 to the n. Or I might write it as, well, I should say, for n greater than or equal to 1, just so that I know where to start my sequence. Or I might say b sub n is equal to 1 over 2 to the n. Or I might add on the notations, n equals 1 to infinity, like that. We're typically going to be dealing exclusively with infinite sequences, because finite sequences, we don't stand to learn much from those. But what we are interested in is whether a sequence converges or diverges with its values. And this is the same kind of definition of convergence and divergence as we've had before. We're going to have a limit. So a sub n, for example, a sub n is essentially random digits between 0 and 9. B sub n, however, is a lot more controlled. Because this is, if I start at 1, this is 1/2, 1/4, 1/8, 1/16, 1/32. We can tell that they're clearly shrinking. They're getting smaller and smaller fractions every time because I have a 1 in the numerator and large numbers in the denominator. Dot, dot, dot. So, since a sub n is kind of random, I would wager that that's something that diverges. But b sub n has shrinking values. And so what I want is some kind of a notion of convergence for sequences. And we have such a definition. So we say a sequence a sub n converges to a limit L if, comma, then our favorite Greek letters come up, for any epsilon greater than 0, there exists a threshold term n, actually no, that's big N, such that if n is larger than big N, then a sub n minus big L is less than epsilon. So you might recognize that this is a lot like the definition we used in section 2.4 for limits. And that's because that's exactly what we're doing. So we'll write the limit as n goes to infinity of a sub n is equal to L. So what this definition essentially says is that if I fix a margin of error, epsilon, you pick a margin of error, then eventually I can go far enough into my sequence so that if I chop it off, everything after that point falls inside of the margin of error. So my b sub n was equal to 1/2 to the n, from n equals 1 to infinity. So this would be, if I wanted to find out if b sub n converges, I would write the limit as n goes to infinity of b sub n is equal to the limit as n goes to infinity of 1/2 to the n. But as n goes to the infinity, I end up having 1 divided by infinity, so this actually goes to 0. So I would say that b sub n converges to 0. On the other hand, if I really wanted to do one of these using the definition, let's say c sub n is equal to, n over n plus 1. And that can go from 1 to infinity. Then what I would do is I would fix epsilon greater than 0. And my task would be to find a big N. That would make my terms c sub n minus L less than epsilon for all n greater than big N. Now my L, I think, if I have very large numbers, I think that this limit is going to be equal to 1. So this turns into one of those 2.4 problems where we have an idea of what the limit should be, but we have to verify it using the definition. So let's see if c sub n minus L would be n over n plus 1 minus I think L is 1. This is the same thing as n minus the quantity n plus 1 divided by n plus 1, if I find a common denominator. But that leaves me with n minus n. Those cancel, so I have minus 1 over n plus 1. Or, since it's an absolute value, I could just ignore the negative and say this is 1 over n plus 1. But this is supposed to be less than epsilon. And these n's are supposed to be larger than some big N. So if I replace that, I'll have a smaller denominator and a therefore bigger fraction. But I need to find out what this big N is in terms of epsilon. So if I do a little bit of work on the side, if 1 over big N plus 1 is supposed to be less than epsilon, maybe they won't be equal depending on what I choose. That means that big N plus 1 should be larger than epsilon. No. Silly. 1 over epsilon. Big N plus 1 would have to be larger than 1 over epsilon. Which means big N would have to be larger than 1 over epsilon minus 1. So again, if I replace that in this fraction, I'll have 1 over epsilon minus 1 plus 1. Put some parentheses there. But if I simplify that fraction, I end up with epsilon. So it's really kind of gross, but this is finding a limit of verifying the limit of a sequence with the definition. Fortunately, we'll never have to do it, because we can just use limits. And specifically, we have something even better. If f of x, if the limit of f of x, as x goes to infinity, is equal to L, and f of n is equal to a sub n for terms of a sequence, a sub n, then the limit as n goes to infinity of a sub n must be equal to, well, technically it's the limit as n goes to infinity of f of n, which is literally just a letter change from the previous limit, so this must be equal to L. So what this says is, in order to find the limits of these sequences, we're going to be using everything from chapter 2, basically. So what do we have there? We have 2.3, which is all of the limit laws and the squeeze theorem. 2.5, which is continuity, but all we really get out of that is you can move limits in and out of continuous functions, and the evaluation theorem, or not evaluation theorem, but the direct substitution. But that's also covered in section 2.3. And then section 2.6, which dealt specifically with infinite limits, as well as sections 4.4, which is L'Hopital's rule. And this is going to help us take care of a heck of a lot of problems. For example, if I wanted to find, I'll say this is d sub n, this is equal to sine cubed of n multiplied by the natural log of n plus 1 over n. And that goes from n equals 1 to infinity. Then the first thing I should do is, while I'm looking for the limit, d sub n converges if the limit as n goes to infinity of sine cubed of n, natural log of n plus 1 over n, exists. That's essentially exactly what we get from that theorem. Which means the first thing I should do is translate this to real numbers. A lot of people are a huge stickler for this step, changing the n's to x's, even though it's just a change of variable. Whoops. Changing to x's, natural log of x plus 1 over x. So I have to solve this limit. But we've encountered limits just like this in the past, in the previous class in fact. So I recognize this might be a squeeze theorem problem because I have a sine and I have something I don't like. So since sine of whatever is between negative 1 and 1, that means sine cubed, of whatever should still be between negative 1 and 1. So the limit as x goes to infinity of sine cubed of x times the natural log of x plus 1 over x, this should be less than the limit as x goes to infinity of a 1 times natural log of x plus 1 over x, and it should be larger than the limit as x goes to infinity of a negative 1 times the natural log of x plus 1 over x. But I can evaluate these limits. This is equal to the negative 1 factors out from limit laws, and the limit moves in because the natural log is continuous, so this is the natural log of the limit as x goes to infinity of x plus 1 divided by x. And there's a couple of ways I could go about this one. I could either split the fraction and have 1 plus 1 over x to get a limit of 1, because 1 over x as x goes to infinity is 0. Or I could divide the top and the bottom by x and achieve the same result. Regardless, we should recognize this one as being equal to 1. But the natural log of 1 is equal to 0. And similarly, the other side, I have exactly the same result, except I have a 1 times the natural log of 1 as my bottom line, which is still equal to 0. So since I have a 0 on the right and a 0 on the left, this must be equal to 0 by the squeeze theorem. Therefore, since that limit existed, d sub n converges to 0. As a corollary to the squeeze theorem, not for limits, for sequences, we have absolute convergence for sequences. What that means is if the limit as n goes to infinity of the absolute value of a sub n is equal to 0, then so must be the limit as n goes to infinity of not absolute value, but regular a sub n. And we can see that pretty quickly because the limit as n goes to infinity of a sub n must be less than or equal to the limit as n goes to infinity of, let's see here, the absolute value of a sub n. But it also must be larger than the limit as n goes to infinity of negative 1 times the absolute value of a sub n. So a sub n is basically swapping between positive and negative values, so it must be below strictly positive values and above strictly negative values. But we know from assumption that this is 0, and likewise this would be negative 1 multiplied by 0 in the end. So this has to be 0 by squeeze. So keep an eye out to see if taking the absolute value will simplify your problem. So some special sequences we'd like to keep an eye out for. Limit then goes to infinity of 1 over n. Well, I shouldn't write the limit. A sub n equal to 1 over n equals 1 to infinity. This is called the harmonic sequence. And that limit is 0. B sub n, if I have a negative 1 to the n power divided by n, from n equals 1 to infinity, this is called the alternating harmonic. Now it's alternating because the n's, the indexes to my sequence, they are integers. Whole numbers. So if I have negative 1 to the 1, I get negative 1. If I have negative 1 squared, I have positive 1. If I have negative 1 to the 3, I have negative 1. It alternates between negative 1 and 1 depending on whether or not n is odd. So this, especially by the corollary we just wrote, since the absolute value of this, the absolute value of negative 1 and 1 is 1, since the absolute value converges, the alternating harmonic must converge. And then we have geometric sequences. So I'll say C sub n is geometric if C sub n plus 1 divided by C sub n is equal to r for all n. This r is called the common ratio, but what it says is that each new term is equal to r times the previous term. Or specifically, C sub n plus, or C sub n in general, I should say, is equal to C sub 0 or C sub 1, wherever you start, times r to the n. So we'll typically write this like C sub n equal to a times r to the n equals 0 to infinity. Now, some books might choose to start this at 1 and change the power, or it doesn't matter. All of it can be worked around. Now these converge if r is less than or equal to 1, and that fits in absolute values. Certainly if r is equal to 1, then I have a constant sequence, and that's very boring. If r is smaller than 1 in absolute value, then we can show with a limit, we might have to use some logarithmic techniques, but we can show with the limit that that converges to 0. However, if r is larger than 1, then we're basically taking a number larger than 1 and multiplying it a whole bunch of times, and it's just going to keep getting bigger and bigger and bigger. So we'll say C sub n diverges. There are some other sequences, actually a very large class of sequences, called recursive sequences. And they're called recursive because, how should I say this? What letter am I using? D sub n is recursive if D sub n plus 1 can only be determined using previous terms. So D sub n plus 1 is some combination of D sub n minus 1, all the way down to the first term. So a very popular recursive sequence is the Fibonacci sequence. Let's see if I spelled that right. Fibonacci. There we go. So Fibonacci sequence, f sub n. Actually, this is recursive, so I should say f sub n plus 1 is equal to f sub n plus f sub n minus 1. Where f sub 0 equals 0 and f sub 1 equals 1. And how does this sequence work is if I want f sub 2 is equal to the previous 2, so that's 0 plus 1, which is 1. F sub 3 is equal to the previous 2, 1 plus 1, which is 2. F sub 4 is equal to 2 plus 1, which is 3, etc. So f sub n is equal to 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, etc. And we can tweak this because all that's determined, or what determines these terms, is really how you start. So a generalized Fibonacci or Gibonacci is one where you change the first two terms to some other numbers. The difficulty, however, is oftentimes recursive sequences can be a bit more difficult to determine whether or not they converge. But we are not without hope, because we have a theorem which will aid us in general for almost all sequences. But we need some definitions. So we'll say a sequence is monotone or monotonic if it is strictly increasing or strictly decreasing, or it does so after only finitely many terms. It doesn't matter what happens to the first couple 100,000 terms, but after that I want it to be going down or going up all the time. So that is a sub n plus 1 is greater than a sub n for every n bigger than big N. This is increasing. Or a sub n plus 1 is less than a sub n for every n bigger than big N. This is for decreasing. We'll say a sequence is bounded above if, for some m, a sub n is less than m for all n. Now, I don't have to do an eventually thing here, because after finitely many terms, there exists a maximum value and a minimum value, because these sequences are supposed to be real valued, and infinity is not a real number. So every term of every sequence is finite. There's a real number I can assign to it, but as I take them off towards infinity, my sequence might be growing infinitely without bound. But I like to know if it's bounded above, which means none of my values ever reach past a certain ceiling. And likewise, I can be bounded below. If for some little m, a sub n is greater than little m for all n. Which says pretty much the same thing as bounded above. If I look down, then I have a minimum value, and I never go lower than some certain value. Now, when I combine these, I actually get a very powerful result called the, I guess here they just call it the monotone convergence theorem. But we do need the bounded result. So we'll call this the monotone convergence theorem. If a sequence is bounded and monotone, then it converges. Now, when I say strictly just plain bounded, it means a bounded above and below, but we have special cases of this. Because we don't need totally bounded, even though every sequence we deal with will end up being totally bounded. Increasing plus bounded above means convergent. Because I'm constantly going up, but I can never reach past a certain ceiling, I must converge somewhere. But this is not necessarily at the bound. I might choose the bound poorly, but I can easily verify, for example, my sequence above where I use the squeeze theorem, I can easily verify that none of those values goes above 2. That's probably not a very good example because that's not a monotone sequence. We'll look at b sub n instead from before. 1 over 2 to the n was decreasing, and it was bounded below. But it's bounded below by 0. I could have said it's bounded below by -1, and certainly none of those b sub n's are ever negative. But since it's decreasing, and none of them are negative, I know that it's bounded below and decreasing, so by the monotone convergence theorem, it must converge somewhere. For any sequence, it will be easy to find the bound, which will match up with the limit. But for several, perhaps recursively defined sequences, it might be very difficult to find exactly what the limit is before being able to tell whether or not it's bounded. And there's definitely some of those in the examples. And likewise, decreasing plus bounded below would also give me convergent. So an example of a use of this, the book does this example, but it doesn't use it using the theorem. Let's let a sub n be equal to n factorial divided by n to the n. Oops. N to the n, there we go. That goes from n equals 1 to infinity. Oh, actually, why don't we start at 0? No, I can't start at 0. That's silly. I can't have 0 in the denominator. I'm cheating over here. So we'll note that n factorial is a recursively defined function. It's n times n minus 1 factorial, or n factorial equals n times n minus 1 times n minus 2, n minus 3, dot, 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 all the way down until I get to 3 times 2 times 1. So it's the product of all of the integers up until n. But there is a problem with this function. N factorial is not defined for any other numbers. So this is a problem which I cannot translate to our chapter 2 limits. So I cannot convert to the limit as x goes to infinity of x factorial over x to the x, because x factorial is not defined for numbers like 1/2 or pi or the square root of 2. So I won't be able to find this one just by using a regular limit. The book gets around this by setting up a squeeze theorem for this problem, but I would much rather do it using the monotone convergence theorem. So n factorial, first I'd like to see if it's increasing or decreasing. Depending on your functions, there's a couple of ways to do this. For example, if I could convert it to a continuous function, I might try to take the derivative to find out if the derivative is generally negative or positive. But again, since I have n factorial, I certainly can't take a derivative of a function that's not continuous. So what I'll do is I'll try two general terms. The n plus 1 term would be n plus 1 factorial divided by n plus 1 to the n plus 1. And the n term is n factorial over n to the n. So the question is, which is bigger? If the n plus 1 term is bigger, then let's see, that will mean my sequence is increasing because it's bigger than the previous term. However, if my n term is bigger, that will mean my sequence is decreasing because the next term was smaller than the previous. So I have more things I can look at the n plus 1 term. This is equal to n plus 1 times n factorial. That's what the factorial means. I can factor that off. And on the denominator, this is n plus 1 multiplied by n plus 1 to the n, letting me cancel those. Now it's a lot easier to compare these. N factorial over n plus 1 to the n, because the numerators are now the same, but the denominators are different, and I wrote it wrong. So let me fix that. N to the n. Now here the denominator is larger, so I actually have a smaller fraction. So here, did I call this a sub n? Yes, I did. Here we see that a sub n plus 1 was smaller than a sub n. So my sequence is decreasing. Now the other thing I need for the monotone convergence theorem is I need to show that it's bounded. Or I need to show at least that it's bounded below. Fortunately, n factorial is greater than 0. Actually, by definition, its minimum value is 0. Actually, you know what? I take that back. It's always greater than or equal to 1. The minimum value for n factorial is 1. So if I had 0 factorial, that would default to being 1. And if I had negative 1 factorial, then that's basically kind of cheating. So I just make that equal to 1 as well. And similarly, not n plus 1, but n to the n is greater than 0, since n is greater than 0. It's also very poorly defined if n is less than 0. So my a sub n's are all positive, so it's bounded below. So by the monotone convergence theorem, a sub n must converge. Unfortunately, it doesn't tell me where it converges. The monotone convergence theorem will not say where, but it will tell me that it does. So I would have to find some other technique of finding out where these converge to. Again, this particular sequence, the book uses the squeeze theorem for, and the squeeze theorem will tell you where it converges. So let's do another one where we can get a better idea of whether a sequence converges or not. Let's suppose that b sub n is equal to, we'll have root 2, we'll have root 2 plus root 2, we'll have root 2 plus root 2 plus root 2, etc. So b sub n plus 1 would be equal to, if I'm reading this right, the square root of 2 plus b sub n. This is another of those recursive sequences. I don't think this is one of the ones in the book, but it does have some similar ones. So first I want to find out if it's increasing or decreasing. It looks to me like this is an increasing sequence. So it'll actually be pretty easy to tell if this one is increasing, because I won't be using the definition of the terms exactly, but b sub n plus 1 is equal to square root of 2 plus b sub n, whereas b sub n is equal to square root of 2 plus b sub n, minus 1. So this over here is equal to the square root of 2 plus the square root of 2 plus b sub n minus 1. But if I follow the pattern, this one is equal to the square root of 2 plus square root of 2 plus square root of 2 plus square root of 2. I have a total of n 2's. Versus this one has a total of n plus 1 2's. So if I write these out, comparing what's inside of them, I have root 2 plus root 2 plus root 2 plus root 2 plus root 2. 1, 2, 3 up to n 2's, and this is the last 2. Versus over here, there's the square root of 2 plus the square root of 2 plus the square root of 2 plus plus square root of 2 plus 0. And here I have n 2's. So, it's really kind of ugly, but since 2 plus the square root of 2 is larger than 2, this sequence is increasing. I would also be able to determine this using induction, which is a bit of a cleaner way to set this up. So induction says that, well, if it works once, and anytime it works the next time, then it must work all of the time. So it's set up like this. I have some base cases to show that it's true at least once. B sub 1 is equal to the square root of 2. B sub 2 is equal to the square root of 2 plus the square root of 2. But since 2 plus the square root of 2 is bigger than 2, that must mean that the square root of 2 is smaller than the square root of 2 plus the square root of 2. Not terribly complicated. So this means that, or this implies b sub 2 is larger than b sub 1. If I try it again, b sub 2 equals the square root of 2 plus root 2, then b sub 3 is equal to root 2 plus root 2 plus root 2. However, since 2 plus root 2 is bigger than 2, the square root of 2 is smaller than the square root of 2 plus root 2, which means 2 plus root 2 is smaller than 2 plus root 2 plus root 2. Oh boy. Which means the square root of 2 plus root 2 is smaller than the square root of 2 plus root 2 plus root 2. Which means that b sub 2 is smaller than b sub 3. So according to these two cases, it looks like I'm going to have an increasing sequence. So induction step. Suppose b sub n is increasing for each term up to n equal to k. Then I want to show that it's again increasing from k to k plus 1. So b sub k plus 1 is equal to the square root of 2 plus b sub k. But b sub k is equal to the square root of 2 plus b sub k minus 1. But since b sub k is greater than b sub k minus 1, that means the square root of 2 plus b sub k would have to be larger than the square root of 2 plus b sub k minus 1. Which means that b sub k plus 1 is larger than the square root of, no, not square root, is larger than b sub k. So I've proven using induction that this is increasing for all terms, because for any of the base cases I've checked, I have now done work to check every case after that. I just have to reread this argument however many times if I want to check. So it's an increasing sequence. Now I should determine whether or not it's bounded above. I've actually checked that monotonic property twice, but now for bounded above, I'm going to exclusively need induction. I have no idea what this is going to converge to, but I can take a guess at what it's bounded above by, because I just have to try. So let's suppose, or maybe not suppose, but let's consider an upper bound of 4. B sub 1, which is equal to the square root of 2, is certainly less than 4. And b sub 2, which is equal to the square root of 2 plus the square root of 2, is certainly less than the square root of 2 plus 4, but that's equal to the square root of 6, which is also less than 4. But I'm thinking, now that I've done a couple of steps, maybe 2 is a better bound. Certainly give that a shot. B sub 3, b sub 3 is equal to the square root of 2 plus square root of 2 plus square root of 2. But, I mean, that's technically equal to the square root of 2 plus b sub 2, but I know that b sub 2 is less than 4, so this is less than the square root of 2 plus 4, which is equal to the square root of 6, which is again less than 4. So I think I see the pattern I'm going to need to do for the induction step. I should label my base cases. We'll suppose that b sub n is less than or equal to 4 for all n less than or equal to k. Then b sub k plus 1 is equal to the square root of 2 plus b sub k, but I have just assumed that b sub k is less than 4, so this is less than the square root of 2 plus 4, which is equal to the square root of 6, which is less than 4 for sure. So by induction, all of them must be less than 4, because I can just redo this process for every next sequence term. So by MCT, b sub n is bounded decreasing. No, I'm sorry. We found it was increasing. And so it must be convergent. Well, we can actually try to find out what this does converge to, because we know that it converges. We know that the limit as n goes to infinity of b sub n is equal to, there's some number out there, it's equal to L. But I know that the limit as n goes to infinity of b sub n, well, the same thing as b sub n is 2 plus the square root of 2 plus b sub n minus 1. That must be equal to L. But if the limit as n goes to infinity of b sub n is equal to L, that must mean at the same time that the limit as n goes to infinity of b sub n minus 1 would have to also be equal to L. Because infinity minus 1, I mean, you're still going to get to the same spots, just ever so slightly later. So this means if I take this in here, I can move the limit to the inside of the square root. The limit of a constant is constant. So I have the limit as n goes to infinity of b sub n minus 1 right in here. That's equal to L. But so is this. So I now have an equation, 2 plus L is equal to L. So I now have an equation, the square root of 2 plus L must be equal to L itself. And I can solve this. I have L squared equals 2 plus L, or L squared minus L minus 2 equals 0. I wonder if that factors. If I have L, let me think, minus 2 and L plus 1, right? So this says that L is equal to 2 or L is equal to minus 1. Well, L obviously can't be equal to minus 1 because that's negative. All of my terms were positive, and it was an increasing sequence, so that's just totally silly. Which means that L equal 2 must be my appropriate limit. And certainly that fits with what I observed earlier. I think if you used 2 for your upper bound, you would have had a perfect choice. So b sub n converges to 2. There's a lot of interesting things we can do with some of these sequences, and we're going to need them for some of the tests for series in the future sections. So definitely give some of these weirder ones a shot, because they can be really fun to do.